Hello, friends. Welcome to the ATC Double Cut. I am Micah Woods, and in this episode, I'm going to discuss 3 recent blog posts. I have been writing blog posts faster than I have been recording podcasts about them, but now that I have returned home from a long multi-month, multi-Pacific flight, trans-Pacific flight, and multiple country trip, now that I'm back at home, I hope to have a bit more regular schedule with recording podcasts, and I'll get up to date with all of the latest blog posts, giving the double cut treatment to them, which means that I explain in words what I was thinking when I wrote them and why I think these topics are worth your time to read about and why I think you will learn some useful information by reading these. In these blog posts, the 3 that we're going to talk about today are related to turfgrass nutrition, soil testing, and how much the grass grows, and specifically how much the grass grows in the springtime or the spring growth flush. All of these seem to me to be quite interesting, and we can get started talking about what these posts are. I will put a direct link to each one of these posts in the show notes so that you can get more information about these, look at the cool charts, and study the information. The first post that we'll talk about has a title, Mehlich 3 Soil Test P in Sand Root Zones. Mehlich 3 is a soil test extraction method. It is what is called a universal extractant, which means it works on a lot of different soil types, and it means it extracts a lot of different nutrients. It's a really useful soil test extractant, and it is in common use in the United States, not so common in Europe or in South Africa or in Australia, although I know some labs can run this test, and it's just a particular extraction solution. It's a chemical solution that you mix with the soil to extract nutrients. So Mehlich 3 is a common one in the United States, and I'm referring here to Mehlich 3 Soil Test Phosphorus in Sand Root Zones. If you look at the top of this post, you can see that the Hugo software that I used to create the website, it has calculated that based on the word count in this post, it is a 6-minute read. And that's a little bit longer than the average post that I write on the website. Usually, recently, I've been writing things that I notice are often like a 2-minute read. This one is a 6-minute read, so that means that it is something substantial. There is a substantial amount of information there, and I want to explain why I put this substantial information there and why I think it's useful for you as you manage turfgrass to understand a bit more about Mehlich 3 Soil Test P in Sand Root Zones. Number one, the first reason why it's important to understand about phosphorus is because phosphorus is one of the macronutrients. People pay a lot of attention to nitrogen. They pay a lot of attention to potassium. Those are the other 2 macronutrients. And I think that phosphorus is the one that gets the third most attention out of the macronutrients. So nitrogen gets the most, potassium gets the next most. And I think for most people, the one that gets the third most amount of attention is phosphorus. And I think the reason for that is because we all know when we took our turfgrass nutrition classes or our soil fertility classes, we learned that phosphorus is immobile in soil. Phosphorus doesn't really move in the soil. So when you put a phosphorus fertilizer application into the soil, or you spread that across the turfgrass and that phosphorus goes down into the soil, the phosphorus doesn't really move. The phosphorus is held in the soil. So we can think of phosphorus, by applying a phosphorus fertilizer to the soil, it instantly becomes a slow release fertilizer. Whereas with nitrogen or potassium, they either have to be formulated as a slow release fertilizer or they will be susceptible to leaching. And phosphorus, we don't really think of it that way. Phosphorus, we put it and then the soil holds it and then the grass can use it over time. So I think people don't worry about phosphorus too much because they just assume that the soil has some amount of slow release phosphorus that will make itself available to the grass over time. I want to explain what the real situation is. And to do that, I looked in this post at a lot of soil test results. I said in the very first section, soil test phosphorus is present across a wide range in golf course putting green root zones. I looked at ATC soil test data from putting greens for the past 5 years. That's 1,773 soil test results, over 1,000 soil test results, closer to 2,000 than to 1,000. All of them using the Mehlich 3 extractant, so we know that they're all going to be expressed on the same scale. And of those 1,773 soil tests from putting greens for the past 5 years, the median value is 46 parts per million. That means half of the samples, more than 800 samples, are above 46 parts per million, but also more than 800 samples are below 46 parts per million. So there's a spread that is, it has a median at 46 parts per million. The mean, which is the average, if you sum all of the values and divide it by the number of values that were summed, that is the arithmetic mean. That is 58 parts per million, and that's higher than the median, which is typical for soil test data. And the minimum is 4 parts per million, which is quite low. And the maximum is 313 parts per million, which is quite high. And I made a chart that I gave the title, Mehlich 3 Soil Test Results, Most Recent 5 Years from ATC's Putting Green Data. If you go to the blog post, which there will be a direct link to in the show notes, if you go and look at that, you will see a scatter plot of soil test results with 1,773 of them plotted as little circles on the plot. And on the y-axis, from the bottom going at 0 parts per million all the way up to above 300 parts per million, you see the scale of soil test results. There are not so many up around 200, 250, 300. And again, the median is at 46 parts per million. So we've got a full half of the samples go from 4 parts per million up to 46 parts per million. And then we have another half of the samples that go from 46 parts per million up to 313 parts per million. So there's a big difference in scale going from 4 to 46. That's a difference of 42 parts per million. So within that range of 42 parts per million, from 4 parts per million, the very lowest, up to the median of 46 parts per million, that's where half the samples are. And then you've got another half of the samples in this data set that go from 46 parts per million up to 313 parts per million. And that is something like 260 parts per million. That's what the range is that those are distributed in. So those are they're spread out more loosely. So basically what that means is soil test phosphorus in golf course putting greens root zones is all over the place, and a lot of the samples are less than 46 parts per million, which is good to know that, because as you get lower than 46 parts per million, you can start to expect that you might see some growth restriction. You may not see deficiency symptoms, but I think if we define deficiency symptoms as growth restriction, then you're probably seeing that as you get down around 30 parts per million, 25 parts per million, 20 parts per million. The grass is probably growing less than it would if it was supplied with more phosphorus. So I think it's really important to know what your phosphorus level is. Is it something that you should be worrying about, or is it something that you can just completely ignore for a while? So that's what I showed in this first chart. And I think it's useful to know what other people's phosphorus levels are. So if you do your soil test result, if you do a soil test and you check by Mehlich 3 and you find that you are at 50 parts per million, you know that you're a little bit above the median. If you find that you're at 100 parts per million, you are considerably above the median. And it's useful to know relatively how much phosphorus is in your soil. So I showed that, and then because there's such a range, I wanted to show the rate of phosphorus depletion, because this is not something any of us got taught in school, I don't think. If you got taught this in school, please send me a message. I would love to hear it. I didn't learn it this way in school, and this is something that I have come to calculate myself, which is the rate of phosphorus depletion. I explained in this post how I use soil testing to make a fertilizer recommendation. And I wrote in the post, I said, I use soil test results to make a site-specific fertilizer recommendation using the MLSN method. The amount of phosphorus recommended is site-specific. There's no specific cutoff value at which phosphorus fertilizer will or will not be recommended. The expected plant use of phosphorus and the duration of time over which the recommendation is made will find how much phosphorus will be recommended. And I explained that the way that this math works out is for a lot of these greens in this data set, remember, a full half of them were above the median of 46 parts per million, and some of these are above 100 parts per million. Some of them are above 200 parts per million. A few of them are even above 300 parts per million. And for those kind of soils, when there's that much P, when I work through the math, a lot of those greens in the data set, they get a recommendation of, quote, no P should be applied for the next year, end quote. And so I looked up for 3 golf courses where I have a long timeline, and by long timeline, I mean multiple years of soil test results and multiple years of making the recommendation, no P fertilizer should be applied for the next year. And for all of these courses, I expect that the amount of phosphorus fertilizer applied has either been none or very little in response to that recommendation. So I made a chart. I gave this chart the title Actual and Expected Decrease in Mehlich 3P. And all 3 of these golf courses, which I labeled as Golf Course 1, Golf Course 2, and Golf Course 3, all 3 of them had a starting soil test phosphorus value above 100 parts per million. And then over time, I calculated how the phosphorus decreased when it wasn't applied as fertilizer. And I think that this is important to understand because I can't make that recommendation forever. I can't keep making that no phosphorus fertilizer should be applied for the next year recommendation. I can't make that recommendation forever because the grass uses phosphorus. It uses phosphorus from the soil. So the next year when you test, the soil test phosphorus goes down. And if you make that recommendation again, no phosphorus fertilizer should be applied, and then the grass grows for another year and you test the soil again the next year, what you find is the soil test phosphorus will have gone down. So when you have the soil test phosphorus in the range of 40, 50, 100, 200, 300 parts per million, this is the type of actual and expected decrease that we observe. And what I show in this chart is that for Golf Course 1, the soil test phosphorus went down over a 5-year period from 111 parts per million down to 68 parts per million. And I showed a dashed line that is based on how much nitrogen was applied at that site and based on the grass species, the phosphorus content of the leaves in that species, given the amount of nitrogen that was applied, this is how much the expected decrease would be. And that's the part that we don't learn in school. We don't learn what the expected plant use of something is. We tend to get taught that it's typical to apply 4 pounds of nitrogen, for example, or it's typical to apply 60 kilograms of nitrogen per hectare. It's typical to apply 50 kilograms of P2O5 per hectare. It's typical to apply to this type of turf 4 pounds of this element, 2 pounds of this element over the course of a year, or per application, we tend to apply like this. But we don't tend to get taught what the use rates are. And if you match the use rates to how the grass actually does use the nutrients, and we can check that by looking at how the soil test levels go down, then we can have a more refined and a more precise control of how the grass is supplied with nutrients, and we make sure that we're supplying the grass with all the nutrients that it can use. So I looked this up for golf course 1. The dash line almost matches exactly with what actually happened. I predicted that it would go down to about 68 parts per million from that starting point of 111, and it did. Then for golf course 2, it started off at 184 parts per million. That's what the soil test phosphorus was back in 2013. On average, it was 184 parts per million. And going up to 2022, it went down to 66 parts per million. And I predicted that it should have gone down to something like 95 parts per million. So going from 184 down to 66 over a 9-year period, over a 10-year period, it went down from 184 to 66. It went down a little bit more than I would have expected. At golf course 3, the phosphorus started at 201 parts per million in the soil, and it went all the way down to 22 parts per million, which is just above the MLSN guideline. In 2021, it was down to 22 parts per million, and I would have predicted over that entire period, it should have gone down to about 55 or 60 parts per million. So what we can take from this, looking at these 3 golf course examples, in the range, when we're dealing in the range of 100, 150, 200 parts per million phosphorus in the soil, and we look at how that phosphorus goes down, what we can find is that the soil test phosphorus can go down even a little bit faster than we would have predicted. And that might be because the grass is using a little bit more phosphorus than I'm expecting. It might be because the phosphorus is leaching just a little bit. It might be because the soil test is measuring some different pools of soil test phosphorus. But what we can expect is that when you have high soil phosphorus, it's possible to predict pretty closely how it's going to go down. And we can be confident that we're not going to go from like 150 parts per million in 1 year all the way down to 40 parts per million. It just doesn't go down that fast. It goes down in a way that matches the expected plant use. So that is good to know. But I want you to be aware of something. This doesn't continue. That linear or the predictable decrease in soil phosphorus doesn't continue when the soil test phosphorus gets down around 30 parts per million, 25 parts per million, 20 parts per million. For example, and I didn't show the data here, but many of you know from watching the year-end reviews that I've done with Chris Trittabaugh, the superintendent at Hazeltine National Golf Club in Minnesota. They've got creeping bentgrass greens there, and Chris has been doing soil testing with ATC for the past few years in the autumn. And the phosphorus there is something like 21 parts per million, 20 parts per million the next year, 20 parts per million the next year, 18 parts per million the next year. And based on the amount of nitrogen that's been supplied, we would have expected that the soil test phosphorus would have gone down by 5, 6, 7 parts per million every single year. So if this predictable decrease was happening down at those low levels of soil phosphorus, we would be going from 20 down to 14, down to 8, down to 2, down to 0 in a 4-year period. But that's not how the soil test phosphorus changes. So as the soil test phosphorus is relatively high, it's really predictable what's going to happen with it, and we can make a really accurate fertilizer recommendation of don't apply phosphorus. As you get down to 25 parts per million, 20 parts per million, down around the MLSN minimum or below the MLSN minimum, I can't make an accurate fertilizer recommendation anymore. Now, I can tell you that you're relatively low, and I can tell you that I expect the grass will use this much phosphorus. And this is the recommendation that I give. I say the grass is expected to use this much phosphorus, and if you apply this much phosphorus, that's just going to match 100% of plant use. But some people are trying to deliberately push the phosphorus a little bit low or allow the phosphorus to get low in order to allow creeping bentgrass to have a competitive advantage over Poa annua, because Poa annua needs more phosphorus near the surface than creeping bentgrass does. Poa annua needs more phosphorus. Creeping bentgrass has a more extensive root system and is able to survive and thrive and compete well against Poa annua at lower levels of soil phosphorus. So that's why I've started looking specifically at the location of phosphorus depletion. So the third part of this blog post, I said, I gave that the title of checking the location of P depletion. I wrote, when the soil P is above 100 parts per million, the Mehlich 3 phosphorus went down on 2 out of 3 golf courses at a faster rate than predicted. The point I'd like to emphasize, I'm still reading from the blog post, the point I'd like to emphasize is that the P in the root zone, as measured by Mehlich 3, goes down in a relatively predictable way with only minor deviations from predicted values on an annual basis, although when those annual errors are accumulated over many years, the Mehlich 3 phosphorus tended to be lower than I would have predicted. That is, the soil P went down a little bit more rapidly than I would have predicted. And the root zone I've been referring to is 10 centimeters in depth. But wait, there are more roots closer to the surface. When my recommendation year after year, as the Mehlich 3 phosphorus comes down from 200 to 150 to 100, and when I keep making that recommendation of don't add P fertilizer, the grass will get all the P it needs from the soil, but it is depleting the P near the surface faster. And that's what I realized. And so I've started testing 20% of the greens that I recommend testing for soil nutrients. I like to do at split depths. I like to take the top 2 inches or 0 to 5 centimeters. And I also, on that same core, like to look at the 5 to 10 centimeter depth or the 2 to 4 inch depth. So we can look at what's happening right at the top of the root zone and also look at what's happening just a little bit deeper in the root zone. So I showed a plot here with a good area Mehlich 3 phosphorus at 2 sample depths. And this is at a golf course. That's at one of those golf courses from the previous chart. I showed where I'd made that recommendation. Don't apply phosphorus fertilizer for the next year. There's plenty in the soil. And then the next year I made that same recommendation. And the next year I made that same recommendation. Well, here's what happened after a decade. After a decade of making that recommendation, the Mehlich 3 phosphorus was down to 36 parts per million on average in the top 2 inches or 0 to 5 centimeters. And it remained at 108 parts per million at the 5 to 10 centimeter depth. That's the 2 to 4 inch depth. I also checked the Bray 2 phosphorus. That's another testing method. And there it was down to 21 parts per million at the 0 to 5 centimeter depth. And it was all the way at 138 parts per million at the 5 to 10 centimeter depth. So there's like 3 to 5 times as much phosphorus deeper in the root zone. Or you can say that it's depleted from 300 to 500% more right near the surface than it is down deeper in the root zone. That is something that I find useful to know, because if we look at the average across those two depths, we're still going to be at something like 60, 70 parts per million, which would be above average. And that would be, it would trigger a recommendation of you don't need to apply phosphorus fertilizer this year. But if we get really precise with it, it's quite useful to look at where the phosphorus is in the root zone. And it's something that if you want to push the phosphorus low, I recommend do check where the phosphorus is in the root zone. If you've got a phosphorus that's on average like 50 parts per million, and you could have that, you'd hate it if you had 100 parts per million right near the surface and 10 parts per million down deeper in the root zone. So if you found that out, you could try to remove some of that phosphorus from the surface and move some of that phosphorus down somehow. It's nice to know what the gradient is. So as the Mehlich 3 phosphorus gets lower, it doesn't decrease in putting green soils as rapidly as expected. And as you don't apply phosphorus year after year, you'll find that the grass will deplete it in certain locations based on where the roots are taking phosphorus from. And you can study that, and then you can really manage how you're trying to manage the soil phosphorus, which is an important thing to manage because it is one of the macronutrients. So if you're trying to push the phosphorus really low, I also recommend doing a test plot. And if you do a test plot where you do put some phosphorus, you can check and see if there's any growth response, any color response, any visual response to added phosphorus. And you can see as the grass goes under stress, if you're cutting water or cutting nitrogen or having high heat or drought stress or regulating the growth with a lot of plant growth regulators, no matter what's happening, you'll have an area that you know is supplied with all the phosphorus that the grass can use. And you can make sure that any unexplained stress or unexplained response on the grass, any problems that you're seeing, you can be confident that that's not the result of your strategy of trying to use relatively low phosphorus. So if you do soil testing with ATC, that's the type of thinking that is coming from me. That's the type of thinking that's going into the soil test report. That's the kind of thinking and calculations that I'm making when I am making a fertilizer recommendation. Let's change subjects a bit, and now we'll go to a 3-minute read, and this is about the spring growth flush, and it's about looking at something called the Speedo, and that is something that I've also called the growth ratio, but now I'd like to call it the Speedo because I think it makes more sense to call it the Speedo. Growth ratio is a little bit too generic, I think, and it has too many meanings in terms of business growth or economic growth. And if you tried to do a Google search for it, you're not going to turn up anything. But turfgrass Speedo, you can remember because you can think of perhaps a swimsuit that is covered in turfgrass, or you can just think of a speedometer, and it's something that to me has a little bit more of a name that sticks. And also the numbers. If we multiply the growth ratio times 100, now we have something that is on a scale that goes from like 0 to 500. So 500 as a speed would be really fast, whether we're in kilometers per hour or miles per hour or meters per second or whatever. That's really, really pretty fast. And if we have a more moderate speed, something like 20, 30, 40, 50, or 80, that seems like a more moderate speed. And so the scale is kind of natural in that way. I wrote in this post, which I encourage you to check out. It's called the Spring Growth Flush. Again, there will be a direct link to this in the show notes. Check it out because I put some preliminary information here. This is the first post in a series that is in progress about standardizing the calculation for the Turfgrass Speedo. I wrote that I've been getting a lot of questions about the Turfgrass Speedo, and I've been checking my calculations to make sure I've got a somewhat standardized method to get the Speedo number for any day. And I showed a chart that shows the grass just jumping out of the gate to start the spring. This is from Moss Golf Club near Reykjavik in Iceland. And Bjarni Hannesson, the course manager, shared these data with me. And to calculate this, we need to know the temperature at the site, and we also need to know the clipping volume. So Bjarni has both of those pieces of data, and he shared them with me, and I calculated the Speedo, and it started off at 0 in April because the grass was not being mown. So if the grass has no growth, the Speedo is 0. And the mowing started in early May, and as it did, the Speedo quickly went up above 50, and then it went up above 100, and it peaked at about 250 on May 20th. And then it started to slowly decline to about, at the time I wrote this post, it was in late May. So it seemed like that is a nice representation of the spring growth flush. And what the Speedo is showing is how the grass is growing compared to how you would expect it to grow given the site temperatures. And in this case, the Speedo is showing that it was growing relatively rapidly. I talked with Bjarni, and he'd applied a relatively large amount of nitrogen in the 2023 season. So the grass was healthy going into autumn of 2023, going into the winter. And it is no surprise that when you have healthy grass and grass that's been well fed with nitrogen in the previous year, that you get a substantial amount of growth in the spring. Now, this is not a huge amount of growth in absolute terms because the temperatures there are cool, but compared to how cool it was, the grass was growing a lot, if that makes sense. And that's what the Speedo is. The Speedo is telling you how much the grass is growing compared to how you would expect it to grow given the temperatures that you've had at the site. And it turns out to be really useful because if the grass is growing in temperatures where it shouldn't be growing, then that is going to be an absurdly high Speedo. If your grass is growing in January when the temperatures are freezing, then and you have to mow every week when the temperatures are freezing, that means the grass is growing relatively rapidly. That's going to give you a very high Speedo because the grass is not expected to grow a lot when the temperatures are freezing. And if your grass is not growing in June, if you're in the northern hemisphere in June, that's generally going to be a pretty good month for growth. If your grass is not growing, but the temperatures are quite good for growth, that is an indication that something is a little bit strange. And you would be expecting that the grass would grow, but it's not. And so then you'll have a low Speedo. It turns out that by looking at the Speedo, you can more precisely adjust the amount of nitrogen. And by precisely adjusting the amount of nitrogen, not only do you get better control over the growth rate, which can lead to improved turf conditions, but you can keep the growth rate from spiking. You can get what we always talk about theoretically of what the goal is to just meter out these small doses of spoon feeding so that we get a really consistent growth response. That's what we talk about. But when you measure only the clipping volume to look at what the growth response is, the clipping volume is not taking into account what temperatures you've been experiencing. And the growth ratio just takes it, or the Speedo takes it one step further. It looks at the temperatures that the grass has been experiencing and adjusts the expected growth based on that. So it takes it one step further, and I think that it is a nice innovation that people are getting really good results with. And because people are getting really good results with that, I want to make sure that it's standardized how we calculate it so that when I tell somebody that they've got a Speedo of 38, if they're calculating that for themselves, they don't come back to me and say, hey, how did you get 38? Because I've calculated that I'm at 27, right? It wouldn't really make sense if one person calculates it and gets a 27 and I take their same data and calculate it and get a 38. So that's why, because I've been getting so many questions about it, I said, let me try to standardize this. So in this post, I started explaining how I'm doing this. And I put a heading of how I'm calculating this. And I explained how I calculate two values for each day to get this. One is the 14-day average of clipping volume. I like to calculate the Speedo with a 14-day average. So I'm using a 14-day average of clipping volume. I calculate this by taking the total clipping volume for today plus the previous 13 days, and I divide that by 14. So that's how I get the 14-day average of clipping volume. And I calculate that for every single day. So 14 days ago, I have a 14-day clip average of clipping volume. 13 days ago, I have that. 12 days ago, I have that. I calculate that for every single day. And the second value I calculate is the 14-day average of growth potential. That's the paste turf temperature-based growth potential. And I calculate that as a 14-day average also. So I've got the average daily air temperature for today and for each of the previous 13 days. From those, I use the GP function to convert temperature to growth potential. And then I calculate the 14-day average for each day. And when I calculate the Speedo, I'm not let me try to phrase this very clearly. I'm not calculating a daily Speedo where the Speedo might be 0 on some days where I don't mow. I don't do it that way. I'm calculating the Speedo as from the 14-day average of clipping volume and the 14-day average of growth potential. So every single day in the year, so long as we have less than 14 days between mowing events, the Speedo will always be above 0. And I calculate the Speedo for each day as the clipping volume, the 14-day average of clipping volume, divided by 20 times the 14-day growth potential. And then, of course, I'm multiplying that by 100 to express it in Speedo terms. What I'm not doing is what I called the chaotic turf Speedo, because I showed a chart here, and I would encourage you to take a look at it. If you calculate the chaotic turf Speedo, you get some values that are really high. Like, for example, the first mow of the year at Moss Golf Club would have had a Speedo on that day of 3,591. As I mentioned, it's normal for this to be on a scale of something like 0 to 100 to 200 to 300. It's quite unusually fast to have a Speedo of 3,591, but if you just calculate the Speedo from your absolute clipping volume for that day divided by the growth potential for that day times 20, you can get some really, really high values. And I showed what those plotted like if we would have calculated the chaotic Speedo, which is the daily Speedo. If you calculate that in the chaotic way, for these data from Moss Golf Club, it was over 500 on 1, 2, 3, 4, 5, 6, on 6 of the subsequent mows in the spring of 2024, we would have had a Speedo above 500. And then it drops all the way down to 0 on the days when you don't mow. And I don't calculate those and take an average of it. I find that it works better to take my 14-day average and calculate the Speedo off of that 14-day average. As I wrote to close out this post, I said, I'm not calculating the Speedo every day based on that day's clip vol only and on that day's temperature only. If I did that, days without a mow would have a Speedo of 0. But I'm interjecting live here and saying that doesn't make any sense, because the grass is growing. Once the season starts, once the mowing season starts, the grass is always growing at a certain rate. The temperature is always happening at a certain temperature. So you've got grass growing in response to temperature. And I don't think it makes sense to do this in a chaotic way of going only on days that we mow do we calculate this. The next day it's 0 and averaging it out. I don't think it makes sense that way. So, continuing back to how I closed the post, I said, but the grass is actually growing and it is experiencing weather. It just didn't happen to get mown on a day and the Speedo drops to 0. That's not so informative. Or if I mowed a lot of grass on on a particularly cold day, that could be a massive Speedo. Grass gets mown in starts and stops, but the Speedo should be continuous. In order to have a continuous Speedo during the mowing season, one needs to smooth the data at least as far as the duration between mows. That's how I closed out that post. And to finish up this ATC double cut, we'll go back to soil testing. And the third post that we're discussing today, this has the title, Soil Testing on the Cornell Turfgrass Show. Soil testing on the Cornell Turfgrass Show. And this is a post that you can find a direct link to, and I'll also link to the YouTube video that for this particular episode of the Cornell Turfgrass Show, because I think you'll find it interesting. And the subtitle of this is soil testing the answer to all your problems? And there's a big no to that. And this is a discussion between Frank Rossi from Cornell University and Carl Scamenti from Cornell University. They had a discussion on the Cornell Turfgrass Show that many of you, if you haven't watched this or listened to it already, you'll really enjoy it, because it's all about soil testing, about fertilizer, about MLSN. It's got a discussion of the park grass. All right, just a little technical glitch there, but we're back. The park grass experiment is also discussed, and so many things about soil testing and how people are trying to sell fertilizer, and how soil testing is a bit of a racket if you're not interpreting the soil test properly, because interpreting soil tests in the wrong way can lead to recommendations for fertilizer that does nothing. In fact, sometimes the fertilizer applied might cause problems that you don't anticipate, and you would have been better off not applying fertilizer at all if you're trying to achieve a certain type of turfgrass surface. So Frank and Carl talk about that at length, and they go through a lot of information in only 30 minutes. So I will put a direct link to my blog post, which I want you to read, because it goes into more detail about a distinction between MLSN and SLAN that I think is important. But I'll also put a link to their video so you can watch that if you haven't already. Specifically, this is something that I was listening for as they discussed it, because Carl, when he talks about MLSN, he often explains it in a very simple way of, you just want to keep your nutrients in the soil above MLSN and then everything will be okay. And so it's like, it's just a criterion where you just look at your soil test. If you're above MLSN, that means you don't need to apply fertilizer. If you're less than MLSN, you can think about applying that element as fertilizer. I like to do it in the textbook way, and the textbook way is a little bit different. So I wrote about that in this blog post. I said, I was glad to hear their discussion of MLSN. Carl and I have discussed this before. The proper way to use MLSN is not to simply use the MLSN minimum value as a yes or no criterion for whether an element should be applied as fertilizer. The MLSN minimum value is meant to be used in a calculation of how much of an element is required as fertilizer. And so I talked about why the SLAN ranges are so high, and it's because they don't consider plant use. So the SLAN ranges need to be really high because they could be used in a case where the grass is going to use a lot of nutrients. And they also don't consider time explicitly. MLSN is considering the specific grass at the site, the way that you're managing it, and for a specific amount of time. So it can very precisely make a recommendation for the amount of fertilizer that you need to stay above this minimum value. But SLAN is based on a different way of thinking, and it's not explicitly clear because nobody is really actively maintaining the SLAN project. So for turfgrass, you would really struggle to get a consistent interpretation of what the SLAN values really mean. So I've written about that quite a bit, and I put a long list of blog posts that you can read about what's distinctive about MLSN. And the distinctive thing about MLSN is it is really looking at how much the grass will use, and it's making sure that the grass will be supplied with that. And so I I always like to make that correction and try to encourage Carl to explain it in this way if he can, because that guarantees that you will never have a nutrient deficiency. So in the blog post, I wrote, in plain terms, when you keep the soil at or above the MLSN guideline for an element, you can have a high level of confidence that the grass has access to all of that element that it can use. Basically, you are putting the nutrient management on cruise control, and you don't have to worry about an element possibly being deficient. But you can't just look at, is my soil test above the MLSN level? And if it is, you say, okay, I'm on cruise control. I don't need to apply that because your grass is alive. And I wrote in the blog post, I said, but the grass is alive and using nutrients. Soil nutrient levels are dynamic. And I always recommend using MLSN with that in mind, rather than taking the way one might interpret a soil test using the SLAN method and substituting in MLSN values. Yes, that works sort of, but it's not the way MLSN is meant to be used. For more about this, here's a selection of posts that discuss this issue, and I then went through 1, 2, 3, 4, 5. I listed 6 posts that go through that issue and explain what the proper way is to think about this. So that is the 3 posts that I went through in this episode. You will find a direct link to each one of those, and you will find a direct link to that cool video from the Cornell Turfgrass Show with Frank Rossi and Carl Scamenti, where they talk about park grass and a lot of cool things related to soil testing and fertilizer sales, and really the type of conversation that a lot of people would like to hear. Some real honest speaking from those turfgrass experts. So I will put a direct link to all of these in the show notes, and I will be very glad if you will check out those posts, because I think you will learn things that will help you to manage the grass a little bit better, whether it's actually putting the nutrient management on cruise control, or whether that is something that allows you to get better management of the growth rate and get that consistent spoon feeding where you can adjust the rates based on how much the grass is growing in response to the site temperatures. That is some stuff that is in the way that Carl Scamenti in the Cornell, what is it, the New York State... is it the New York State IPM program? He's got a birdie level. He's got a par level, birdie level, and eagle level type of implementation of techniques. And I think just fundamental, basic MLSN, like the way that Carl explained it, something like that, or just measuring, just looking at the clippings and checking if the grass is growing too much, that's like the par level. And then doing MLSN properly, that is like the birdie level. Measuring clipping volume, that's like the birdie level. And then what I'm talking about here is really estimating plant use, really making full use of MLSN, using the Turfgrass Speedo to adjust your fertilizer applications. That is something that's at the eagle level. So these are things that I'm sure everybody can get use of, and you can either look at this as something and you're like, you know what, I'm happy at the par level, I'm happy at the birdie level, or it's like I'm still figuring out how to make par after par after par with a few birdies thrown in. Maybe I'll try for the Eagles next year. It's good to be aware of this stuff, and it's good to know what people are getting really good success with around the world using these type of techniques. So as always, thank you for watching and thank you for listening. And I will sign off now for ATC from Trong, Thailand. I'm Michael Woods. Bye-bye.